let's take a look at Lee's theorem. We're going to follow the MIT lecture notes as we did last time, and that's because the statement they prove is actually a bit more general than the one in the book. And our proof is going to be actually pretty similar to how we did Engel's theorem, because these theorems are pretty related. So let's take a look at the statement of the theorem. So here we go. Let L be a solvable Lie algebra. Let pi be a representation of L in a finite dimensional vector space. And I kind of added this caveat here. Let L be a finite dimensional Lie algebra as well. Furthermore, suppose L and V are over an algebraically closed field of characteristic 0. Then there exists a weight space for pi with weight lambda. And so before we go into the proof, just some things I want to point out. First of all, we need this algebraically closed field. We need an algebraically closed field to apply Lee's lemma, which we showed in the last video, and that's going to do a lot of the heavy lifting in this proof. The second thing is we need a characteristic 0, and you can find a counterexample, exercise 3, which shows you this. And so the reason we didn't need these assumptions for Engel's theorem was because 0 is always an element of the field, regardless of its characteristic or if it's algebraically closed, and that's the only eigenvalue we have to worry about last time. Whereas this time, we need our eigenvalues to be in the field. And so now let's take a look at the proof. It's pretty similar. And the way we're going to do it is we're going to induct on the dimension of L, just like last time. So proof, induct on dim L. Right? So when dim L is equal to 0, right? The statement is trivially true with lambda is going to be 0 and v sub lambda L is just equal to v. And when I say 0, I really mean the 0 linear functional that sends every vector to 0. Now we're going to, so this is clearly true. So now we're going to move on to our inductive step. Now, assume dim L is greater than 0 and theorem is true for all smaller dimensional Lie algebras. And when I say theorem is true, obviously these smaller dimensional Lie algebras have to be subject to the hypothesis of the theorem. So now we're going to use some facts about L being solvable. So L is solvable implies that L bracket L, so L solvable, implies that L bracket L is strictly contained in L, right? Because then otherwise the derived series wouldn't terminate and it wouldn't be solvable. And so we know that L bracket L is an ideal, so the quotient space L bracket L is well defined, and then we know that this thing is equal to x plus the derived algebra for x and L. So these are just a bunch of cosets. And so this guy is abelian, and it's very easy to see this. You could do it in your head. Take x plus L, I'll just write it out actually, x plus L bracket y plus L bracket L is equal to x bracket y plus L bracket L by definition. And by the definition of the derived algebra, all commutators live in here, so this is simply equal to L bracket L, which is the 0 vector in our quotient space, and so this guy's abelian. Now because this guy's abelian, all subspaces, like as in vector subspaces of L bracket L, are ideals. Right, that's very easy to see. So let T be a maximal proper sub-ideal, I guess. I could just say ideal. So that means that dim T is equal to, let's say, we'll say dim, the quotient algebra is equal to m, then dim T is equal to m minus 1. And we're going to need this later. I'm just going to assume dim L is equal to n. So we have this. Okay? So now we're going to define two maps that are important. The first map is going to be the projection map of the quotient algebra onto T. Right? That's just the vector projection. So I'm going to call it PT that sends the quotient algebra to T, and this is going to be a vector space projection. The second map I'm going to define is going to be PL bracket L, and this is going to be the canonical homomorphism. I would use pi, but we're already using pi for the representation. And so this sends L to its cosets in L mod the derived algebra. So this is the canonical homomorphism. Great. Now we have one last thing to define. We're going to define K is equal to the pre-image of T with respect to the canonical homomorphism. So all I'm saying is that if you take a vector in K and then you apply the canonical homomorphism to it, it gets sent to a vector in T. That's it. Okay? And so what we're actually going to do is K is going to be the fundamental thing of interest here. We're going to show some facts about K and apply the inductive hypothesis to it, and then Lee's lemma, and so on. And so we're going to try to derive some more information about K. So I'm going to leave a little part of this to the viewer, which is to show, or I'll say check that K is an ideal of L, and L bracket L, the derived algebra, is contained in K. This is really easy to do. You're just going to use the definition of an ideal and the definition of the derived algebra, look at the cosets, see they get sent to 0, and everything will work out. It's pretty easy to see. But I'm just going to assume this, and so we see that, so I'm going to put a check here. We see that we have the following chain of ideals. L bracket L contained in K contained in L. Okay, great. So now we're going to, so as I said, this is the guy we want to do induction on. So we want to somehow determine its dimension. So we're going to use the maps we've defined and these various ideals to determine its dimension. So we have that dim, so I'm going to draw a line here. Dim L is equal to n as above. Dim L mod the derived algebra is equal to m as above. Dim T is equal to m minus 1 as above. And then now we're going to let dim K, I'm going to define this to be Q, just so I don't have to write dim K every time. Now we're going to look at the kernels of our various maps. So we have P sub the derived algebra, right? Takes vectors in L, sends it to the coset, and this guy has kernel of dim n minus m, right? This is just an application of the rank nullity formula right here, n minus m. And we're going to consider the composition map pt of p L bracket L. And so this map takes vectors in L and sends it to T, right? First we go to the quotient algebra, and then we project onto the vector subspace. And so this has kernel of dimension n minus m plus 1, right? Because the first guy has a kernel of dimension n minus m, as we saw here, and then once we project onto a subspace that's of codimension 1, we're going to add 1 to our kernel. And so the last thing we're going to map we're going to consider is I'm going to call phi, because this is a big name, and this is going to be this map up here, this map restricted to K. So this is going to be pt of p L bracket L restricted to K. I'm going to denote it like that. And so this simply is the same map, but it sends vectors in K to T. And so by the same logic as above, this has kernel of dimension Q minus M plus 1. Okay, that's great. So now we're going to make the following observation. Observe that if X is an element of the kernel of P sub L bracket L, then X is an element of K. And so this is really easy to see. simply because if x is in this kernel, that means that x is an element of the ideal, and so if x is an element of the ideal, then obviously under this map here, phi, it's going to get sent to 0. And I skipped a step. We want to show it's an element of k, so it's an element of the ideal. And so that means it's in the preimage of T, right? Because this coset L bracket L is the 0 vector, and the 0 vector is in every subspace of the quotient space, and so that means L bracket L is contained in T, and so that X is contained in K. And the reason we want to do this is that if X is contained in K, we can apply phi to it. We can apply phi to X, and we see phi of X is equal to L bracket L as a coset. And so that means that phi X is an element of curve phi. The reason I did this is now we get a really nice statement, which is that curve phi, or rather curve, the projection onto the coset is contained in curve phi, right? And so that means that this guy has dimension q minus m plus 1, and this guy has dimension n minus m. So we have this statement. If this guy is contained in here, then this n minus m is less than or equal to q minus m plus 1. So we get that n minus 1 is less than or equal to q. Okay? So now we want an upper bound. But the upper bound is really easy, right? Upper bound is obviously less than or equal to n. And I'm just going to show that it's actually less than n. Dim k equal to dim L implies that k equals L, right? If q equals n, then k is equal to L. But if k is equal to L, then if you apply the projection, right, this tells us that T, which is the preimage, which is what, well, k is the preimage of T, so if you apply that map, you're going to get to T, would have to be contained, would have to equal L bracket L, right, if we apply this map. And so if L bracket L, if the quotient space is equal to T, then it can't be strictly contained, and so this is actually a contradiction. So this is actually, we have n minus 1 is less than or equal to q less than n. So that tells us that q is equal to n minus 1. And so this step in the proof is actually like one line that gets completely ignored, and it's not entirely obvious, especially if you don't have experience with working with codimension, and it's just not clear as to how they show that dim k is equal to n minus 1. But regardless, I've shown it, and so we have dim k is equal to n minus 1. So this is great. K is an ideal that is strictly contained in L, and so what we can do is we can write L as the follows. L is equal to the direct sum of k with some vector. So this is denoting span y. I usually write span y, but I think I'll stick with the book's notation. So this is equal to y element of L, and y is not an element of k. Right, so we're going to fix this y, and we're going to use it later. So now we have this statement, and now because k is an ideal of L, and L is solvable, k is solvable. Therefore, we can apply the inductive hypothesis. And so this is great. We can apply the inductive hypothesis, and so we know that then there exists a weight lambda element of k star for pi pi restricted to k rather, right, because it doesn't act on k but rather acts on L, such that v lambda k equal to V element of V, pi k acting on, so this is a big K, this is a little k, acting on V is equal to lambda of k acting on V for all little k in our ideal. Right? So this is just by the inductive hypothesis we know that such a vector exists on the restriction of the representation. So now is where we're going to use Lee's lemma, right? K is an ideal in L, and so by Lee's lemma, this subspace of V is invariant under all pi of x for x element of L. Okay, so that's great. And so what we have now is to take this y that we introduced up here, and what we're going to see is that pi of y, right, acting on, by the statement pi of y acting on V sub lambda k is contained in V sub lambda k. Okay? And so what this means is that there exists R element of our field and V not equal to 0 element of V sub lambda k such that pi of y acting on V naught is equal to R times V naught. Okay? All we're saying is that y is not contained in K, right? By up here. So y is not contained in K, but we know by Lee's lemma, pi of y is still going to stabilize this weight space. And since span y is one-dimensional, we don't need a linear functional. We can just use a scalar. So we see that that there is some non-zero vector in here, such that pi of y v naught is equal to r v naught. And so now we're almost done. We're going to define a new linear functional that acts on L rather than K as follows. So define lambda prime element of L star, our dual space on L, as lambda prime of K plus Cy, where C is a scalar. And so any vector in L can be represented as K plus Cy, because we said it was the direct sum of K with the span of Y. And so lambda prime of K plus Cy is defined to be lambda, our weight that we found for K, acting on K, plus C times R. So so let's say for all K in big K and C in F. Okay? This R is above, right? And so clearly by construction, clearly V naught is an element of V sub lambda prime L, right? Since V naught is non-zero, we're done. We are done. Right? So I'm going to leave it to you to check that this is indeed this definition here. It's really easy. If you act on any vector in V, you're going to get that vector, it's easy to check. Just use what we've done so far. And so, yeah, so this is the idea of the proof. It's actually, it looks different from Engel's theorem because we use a different technique to express L as a direct sum as K with the span of some vector. But the idea is pretty much the same. But regardless, we've shown the theorem that indeed this vector exists and this weight space exists. So let's go all the way back up to the top. And so yeah, this is the theorem. So now let's take a look at some of its corollaries that I've already taken the time to prove because they're pretty easy to see. So the first corollary is also known as Lee's theorem, so I've written that here. And so let V, L, and pi be as in the theorem we just saw. Then there exists a basis of V in which x for all x in L, pi of x is upper triangular. So the proof of this is almost identical to how we showed that there is a basis of V in which pi of x is strictly upper triangular for Engel's theorem. And so I've just outlined the proof. What we're going to do is we're going to induct on the dimension of V. First, we're going to show that the statement is true for dim V equals 1. That's pretty easy. And so then we're going to assume the statement is true for all smaller dimensional vector spaces. I've just kind of written that here in a fancy way. And then we're going to use Lee's theorem that we just, well, when I say Lee's theorem, I mean the theorem we just proved, to find a common eigenvector. And then we're going to quotient out that common eigenvector, which by definition is invariant under our representation. And then we're going to consider the factor representation. Then we're going to apply the inductive hypothesis to the factor representation to find the basis for V mod the span of our weight vector. And then and by the inductive hypothesis, there's an upper triangular basis for that guy. And then we consider the preimage of that basis and then union it with our weight vector as follows in this order. And then we find a basis in which all the pi of x are upper triangular. The reason I'm not doing this again is because if you look at the proof how I did in Engel's theorem, it's almost identical. So I leave that to the viewer to check. So now let's look at the second corollary. Suppose L is solvable, then there exists a chain of ideals, 0 equal to L naught, containing L1, containing Ln equal L, such that dim Li is equal to I. This is pretty easy. What we're going to do is we're going to apply corollary A that we just saw and take our Lie algebra to be L, the representation to be the adjoint representation, and then V to be L. And I've had this additional caveat up here so that we can actually apply corollary A, where L is finite dimensional over algebraically closed field of characteristic 0. Anyways, we apply our corollary, and so we find that add x is upper triangular in some basis of L, right? That's what that corollary A just said. And this is true for all add x. And then so suppose this basis is beta equals x1, x2, xn, where dim L is equal to n. Then simply define this chain of ideals to be the span of the first I vectors. So I'm saying L naught is the span of the 0 vectors, so it's a 0. And then L1 is the span of x1, L2 is the span of x1 and x2, Ln equal to L is the span of x1 through xn. And what you realize is that when add x acts on this basis, in which it is upper triangular, you're just going to get vectors contained in Li again. And so that proves corollary B. Pretty nice. And so the last corollary we have is corollary C. Let L be as in corollary B, then for all x in L bracket L, add x, an element of the general linear algebra of L is nilpotent. And then by Engel's theorem, L bracket L is nilpotent. Engel's theorem is actually a bit of overkill. You can see right away that L bracket L is nilpotent, but let's just go through the proof. So by corollary B, right, we can find this chain of ideals in L, right, because we said L is solvable. And then now suppose we can fix a basis for these guys, and so we'll say x1 through xi span Li. So then by corollary A, for all x in add L, add x is upper triangular with respect to our basis x1 through xn. This is our basis for L. Okay? So because all these add x are contained in our upper triangular, add L is a subalgebra of the upper triangular matrices. So if you bracket add L with itself, then it is a subalgebra of the strictly upper triangular matrices, right? Because the strictly upper triangular matrices are the derived algebra of the upper triangular matrices. But observe that by the homomorphism property, add L bracket add L is actually the adjoint of the derived algebra. So the adjoint of the derived algebra is contained in the strictly upper triangular matrices, and so because it's a subalgebra of the nilpotent Lie algebra, it must be a nilpotent Lie algebra. And because it's a nilpotent Lie algebra, then all its elements, right, which are of the form add x, where x is an element of the derived algebra, are nilpotent. And then, obviously, L bracket L is nilpotent. So the Engel's theorem, the word Humphreys uses like a fortiori or something, which means like it's by even more evidence. So Engel's theorem just confirms that we know that L bracket L is nilpotent. So yeah, so that was a lot. And so, nevertheless, I think the most important parts to remember are this part, that pi of x can be made upper triangular, and that you have this weight space. That's really all you need to know when you remember Lie's theorem. So that is the conclusion of this video. Thank you for watching.